Hi everyone. Today I would like to talk about linear function and affine function. This is the second video in the series of video I have about the numerical linear algebra and optimization. Okay, so let's talk about the function. Function is defined usually denoted by the letter F for a function. Let's choose the right color here, right? That its domain is Rn, set of n-dimensional vector, right? We defined that in the last video. If you have not watched the last video, please go ahead and watch them. I will put a link in the description to the last video. So this is the domain of a function, and the R here is a codomain. Sometimes it's used as a range. People talk about the range, but the more technical word is a codomain, right? What is a codomain and what's the range? Let's talk about that. First of all, this R is a set of real numbers, right? Okay, the codomain is a set of possible values for the output, right? And the range is set of values that you can actually obtain. So take this one, this R here as a Y, right, or as f of x, right? In the range means that when you get f of x, there is an x in the domain for that. So for each x, for each f of x, if you have x in the domain, you call that f of x as part of a range, right? Codomain might not be achieved, right? It's set of potential or possible values for the output. So in a sense, range is a subset of codomain. I'm going to write this one with another color. Range is a subset of codomain. Okay, so for example, like the angles around the circle. So for example, the range would be from 0 degree all the way to 360, right? But the codomain can be like 900 degree, 1000 degree, right? So sometimes the range and as a codomain are the same, but always range is a subset of codomain. So here, this R is the actual codomain. Okay, good. Just a little technicality. And now, when this happens, when you have to just get a one value for that, get 2, 3, 2.5, 360, you call this function a scalar value function because you are mapping an n-dimensional vector to a scalar value, right? This is called a scalar value function. Okay, so a little bit more notation. I said sometimes you let x to be x1, x2, all the way to xn, and you define f of x as this, f of x1, x2, and xn. So it's a function of n variables, right? Sometimes for simplicity, just write f of x, right? So sometimes, for example, I have it here as an example. I say f of x, right, means A transpose x. We talked about this dot product in the last video is equal to A1, x1, A2, x2, all the way to AN, xn. So what we actually mean here is this, f of x1, x2, all the way to xn. But sometimes for simplicity, just write x, right? Okay. So this A transpose x I define as a weighted sum of element of x. They are weighted by vector A, right? Like the probability I defined in the last section. It's a proportion, it's a weight. Okay. Now, this inner product is a linear operation, right? It's a linear. You see that you're adding a bunch of numbers. Addition is a linear operation, right? And remember, this A is like a constant, right? It's not, so the domain, the parameter, the variable here is x. So it's linear in x. Okay, good. So it satisfies the superposition principle, which is defined as follows. So this is the definition of a linear function. Any function that satisfies the superposition principle is considered as a linear function. And if a function satisfies the superposition, so if a function is linear, it satisfies the superposition. Okay, this is very important. Now, what is the superposition principle? It says that f of a alpha 1 x1 alpha plus alpha 2 x2 linear combination. Right now, we know what linear combination is. F of linear combination of the components of x is equal to alpha 1 times f of x1, alpha 2 times f of x2 plus alpha n times f of xn. Now, this property usually broken down to two smaller properties. You usually see these properties as a smaller or two properties in literature, namely homogeneity and additivity, right? So homogeneity says that f of alpha x is equal to alpha f of x. You can extract the alpha from this function. And additivity, as the name suggests, says f of x1 plus x2 is equal to f of x1 plus f of x2. If you put them together, you get this superposition principle, right? So now let's talk about why the dot product A transpose X. Why is that a linear function? So by looking at that, it's linear, but let's prove this one. So when you are asked to prove something is linear, or you are asked to verify something is linear or not, you follow the principle of superposition, means homogeneity plus additivity, right? So we define the f of x to be A transpose times x. This is our f of x. We're gonna write f of alpha 1 x1 plus alpha 2 x2 all over alpha 1 xn, right? So we are using this superposition principle. This one. Good. Now, so we know f of x itself is A transpose x. So instead of x argument, we put this long argument, alpha 1 x1 plus alpha 2 x2, right? So this is gonna be the argument that sits instead of x here. So we get A transpose times alpha 1 x1 plus alpha 2 x2 all the way to alpha n xn. Okay. Now we talk about the multiplication of a vector by a constant. So this alpha values are actually constant, right? So you can take them out. You can take it out of the this dot product, right? So what you get this. You get alpha 1 times A transpose x1 plus alpha 2 times A transpose x2 and all the way to alpha n plus A transpose xn. But remember, f of x was A transpose x. So f of x1 becomes A transpose times x1. So therefore, this quantity that you see here is f of x1. I wrote it down here. This is f of x2. This is f of xn, right? Therefore, I get alpha 1 f of x1 plus alpha 2 f of x2 all the way to alpha n f of xn. So this is exactly the principle of superposition. Therefore, A transpose x, which is the dot product between vector A and vector x, is a linear function. Okay, so we prove this one. I wrote it down here for you. What happened? Dot or a scalar product is a linear. Now I have something more interesting. Any linear function can be written as dot product. This is a fascinating result. Any linear function can be written as dot product. Any linear function. Let's take a look at the proof together. So remember I told you that the unit vector in the last video has numerous applications. One of the applications here. I said any vector can be written as a linear combination of the unit vectors, right? So here I'm talking about vector x. I can write it as a x1 e1 is e1. Let me remind you, e1 is 1 is the first element and 0 otherwise, right? The same thing is e2 is 1 is the second element and then 0 otherwise. So x1 e1 plus x2 e2 all the way to xn en. We also saw how you can calculate these coefficients using the projection and the dot product. Now let's plot that in f of x, right? And use the principle of superposition. So instead of x, I will put this expression, right? So you see it here in this line. Now I would say superposition. I get x1 f of e1 plus x2 f of e2 all the way to xn f of e. And well, what is this? Let's take a look at that. I wrote down superposition here. Perhaps this one is no longer. But what is this one? This is A transpose X, where A is just defined like this. F of E1, F of E2, this is just a definition of dot product, right? And X is just X1, X2, Xn. Since I define it as a column vector, let's put it like this. Okay. Great. So this is just A transpose X. So we prove that a scalar or dot product is a linear function. And any linear function, it's very important, any linear function can be written as a dot product. Therefore, from now on, you can also have another definition for linear function. You can say a linear function is a function that satisfies the superposition principle. So I will write down here, linear function satisfies the superposition, satisfies the superposition. 2, it can be written as A transpose X, right? We just saw that. F of X can be written as A transpose X. From now on, you can write linear function as A transpose X without loss of any generality. Okay, great. Now let's talk about affine function. This definition of affine function. This affine function is used extensively in a lot of applications, but people use the word linear function for them. This is like some sort of abuse of notation, abuse of definition here, right? So what is the definition of affine function? I wrote here linear function plus a constant. Yes, affine function is just a linear function plus a constant, right? But in the literature, you see this definition as a linear function as well, right? So for example, y is equal to ax plus b in a scalar domain. This is affine. This is not linear. But you people say that, okay, let's model this problem using linear function. This is just an affine function. So we make sure that we actually distinguish between linear and affine. Okay, good. Now, also affine function satisfies the superposition principle, but not the same superposition principle that linear function satisfies, right? So affine function superposition principle is as follows. You say f of a alpha 1 x1 plus alpha 2 x2 all the way to alpha n xn is equal to alpha 1 f of x1 plus alpha 2 f of x2 plus alpha all the way to alpha n f of xn, given that the alphas, the coefficients, are add up to be 1. So for linear function, they could be any coefficient. For affine, they must add up to 1. Why is that correct? Let's see why is that correct, right? I would like to write the superposition principle for the affine function, and let's see under what condition. If they are correct in general, they are just linear. Why should I call it affine? I want to see under what criterion these coefficient, under what condition on this coefficient or constraint for this coefficient we can have affine, right? So I'm gonna define f of x the same, a transpose x plus b. This is the f of x that I have here. I use this f of x. Now I am gonna use the superposition, means that I'm gonna plug x for this one. So I'm gonna get a transpose alpha 1 x1 plus alpha 2 x2 all the way to alpha 1 xn plus b. Remember the function was a transpose x plus b. Now let's go ahead and extract this constant term outside. We have alpha 1 a transpose x1 alpha 2 a transpose x2 all the way alpha n a transpose xn plus b, right? That's what they have in this line, right? Good. Now I want these to be equal to what? I want this to be equal to this. So this one, what I have here, I would call this equation, let's say equation 1. This is called left-hand side of 1. This is the left-hand side of 1. Now here, this is the right-hand side of 1. I want them to be the same, right? Let's see under what condition they are the same. So here I write alpha 1 times f of x1. What was f of x? A transpose x plus b. So alpha 1 times a transpose x1 plus b plus alpha 2 times a transpose x2 plus b all the way to alpha n times a transpose xn plus b, right? I want them to be the same. Let's expand this. Let's actually calculate this multiplication. So this is what we get for the left-hand side, right? For the right-hand side, when I multiply them, I get alpha 1 a transpose x1 plus alpha 1 times b. I have it here. Alpha 2 times a transpose x2 plus alpha 2b. In a sense, for equality, you see that alpha 1 a transpose x is the same. Alpha 1 a transpose x1, alpha 2 a transpose x2 is the same between left-hand side and the right-hand side. What is missing is that for one of them, we have only b. For the other one, we get alpha 1 plus alpha 2 plus all the way to alpha n times b, right? Why is that? How did I come up with that? This is alpha 1b, this is alpha 2b, this is alpha nb. I just factor from the b. This is b, right? There is no b and it's just b, right? So if you factor from b, you get what? You get alpha 1 plus alpha 2 all the way to alpha n times b is equal to b. It only happens if alpha 1 plus alpha 2 all the way to alpha n is equal to 1. Because we are solving in general case. Sure. You can say it happens when b is 0. But when b is 0, the alphas can be anything, and then they have a linear function. When b is 0, we don't have affine, we have linear function, right? So we just saw that there are two definitions for affine that they are equivalent together. One, affine functions are the functions that can be written as a linear function plus a constant. Two, affine function that support the superposition principle when the coefficients add up to be 1. And we just saw the proof as well. Okay, now check for linearity and affinity. How do we check for that? For linearity, two ways. Check to see whether the function can be written as A transpose X, right? And then find the A and X to make sure that it can be written as the correct form. Or check this superposition principle that I have here, this one, right? For any alpha 1, alpha 2, and alpha n, for any, this is for linearity, it's very important. For affinity, you either can check to see whether you can massage your problem to be written as A transpose X plus B, a linear term plus a constant, or check to see whether the superposition principle holds when the sum of the coefficient is equal to 1. This is for affinity, right? Now, I consider this one as method 1. Perhaps I had to choose 3 methods. So one method is whether you can write as A transpose X or A transpose X plus B. Two method is to check the principle of superposition. And then I consider method 1 and 2 to be the same. Now method 2 I have here by looking at the graph. Right? You can draw that. You can plot it. Perhaps this is like the same as A transpose X and A transpose X plus B. The linear function will pass through the origin. A linear function will pass through the origin. Right? So when x is 0, f of x is 0, because there is no constant term. There is no y-intercept, right? The affine function will not pass through the origin. When x is 0, y is not 0. If y is 0, we get linear then, right? So b is non-zero for affine, right? Okay, so look at these two diagrams. This will show you actually visualize this to affine and linear function. Okay, let's continue now. Taylor approximation. So Taylor approximation is a method to model any function by affine or linear function, right? Any differentiable function, because we are taking differential with respect to x or coordinates of x, x1, x2, so like a vector x, right? So in a sense, sometimes it's known as a linearizing a function near a point x or near a point z. So linearization is used a lot in literature, but yes, we are actually somehow forming a linear function. It's just in this video series, we're gonna use the correct term. It's used for model the linear and affine, right? How do we do that? F of x is our function that we want to model. We write it based on f of z is the point that we are modeling f of x next to that, near this point. Z is the point f of z plus derivative of partial derivative of f respect to x1, because we are taking derivative with respect to multiple components, x1, x2, xn. So we don't use a d operator, we use round of x, f of f, round of x1, calculated at the point z times x1 minus z, right, z1, plus round of f, round of xn, calculated as z, right, times xn minus zn. Okay, good. Now, I explain here this is a partial derivative of f. This is called first order approximation. For a second order approximation, you have some sort of a second derivative on xn minus n square. Right? This is first order approximation. This is what we get. It's usually a very good approximation, the first order approximation. Right? Now I have an example here, what I mean by that. So let's say that we have a two-dimensional vector x, x1 and x2 are the coordinates, and f of x1, x2 is equal to x1 squared plus x2 squared. And you want to model it near the point 1 and 1. So z is 1 and 1. Right? Okay. So you write f of z z is 1 and 1, right? F of z is gonna be 1 square plus 1 square is 2. This is here, f of z plus round of f of x1 is equal to 2x1. Partial derivative of this respect to x1 means that x2 is constant, right? So 2x1 calculated at the point z1, right? 2 times 1 is 1, 2 times 1 is 2 times x1 minus 1 plus 2 times x2 minus 2. You get 2x1 plus 2x2, 1 minus 2 and plus 2 cancel out. You get 2x1 plus 2x2 minus 2, right? So that's how actually you calculate the model the function using a linear or affine. This is affine, right? This is A transpose X, right, plus constant. There is a constant here. Okay. Now, in a sense, this can be in a short closed form solution like this. This linearized, I should not use this, approximated version is equal to f of x. F of z remains as f of z times the gradient. Remember, this is gradient. Gradient of f of z transpose times x minus z. Right. So x and z are the vectors, right? We just saw example. So x minus z is x1 minus z1, x2 minus z2 corresponds to this when you do dot product. And what is the gradient? Gradient is defined as follows. Gradient of f calculated at the point z is equal to gradient respect to each coordinate of x. Partial derivative of f respect to x1 calculated as z. Partial derivative of f respect to x2 calculated as z. Partial derivative of f respect to xn calculated as z. It's good and important to know that the usual gradient usually have the same shape as the vector itself, right? So gradient of f respect to x is a column vector, n by 1. Gradient will be n by 1 as well. Okay, so this is an n by 1 vector. So you can write in a closed form based on, you see, this is the affine function. What's the difference between this? It can be a, and you can take this one as like y. This is a affine function, okay, in general. Now, pictorially, what I've been talking about, this is f of x, this is x. This point is z. You want to model this approximately next to the point z and f of z, right? Okay, good. So what is the slope? The slope is gradient of f calculated as z. The slope is a tangent line, so it's the derivative. And in the univariate case, you have f prime of x usually, right? So here is gradient only. Gradient of f calculated at the point z, right? And it passes through the point z and f of z. We know that we can draw the equation of the line when we have a point on that line and we have a slope, right? So we're gonna go ahead and do that. F of x minus f of z is a y coordinate of a line times, this is a slope, f of z transpose, so we have a vector here, right? Times x minus z, okay? When you manipulate this, you get f of x, f of z goes to the other side, right hand side, and you get this expression. It was the same expression we got here above, right? So number 3 and number 2 are the same. Number 2, we got it using the Taylor expansion. Number 3, we got it using the diagram, using the graph. Okay, so that's what I have for linear versus affine function. We talk about multiple concepts, approximation of any function using linear or affine, the properties of linear and affine, how to check if the function is linear or the function is affine, a couple of definitions of them. And in the next video, I want to talk about the variance, standard deviation, norm, distance, angle, a lot of inequalities as well. So that's it for this video. Thank you so much for listening. See you all in the next